and today we'll be talking about post-quantum cryptography, challenges, advantages, and the impact on data security. So here we have the outline. As you can see, we've got quite a bit to get through in 7 minutes. So we'll talk quickly about the basics of modern cryptography and also the basics of quantum computing. Then we'll run through some of the more important quantum algorithms. We'll talk about quantum resistant algorithms and then the near future. So when we talk about the current state of cryptography, we often talk about symmetric and asymmetric cryptography. So symmetric cryptography makes use of a shared private key, which needs to be exchanged ahead of time, whereas asymmetric cryptography does not require this. So it has a public and private key pairing, which allows for two unknown entities to communicate securely for the first time. It also allows for digital signatures and authentication. So here we have AES and triple DES for examples of symmetric key, and then we have RSA and Diffie-Hellman. So importantly for asymmetric cryptography, all of these algorithms are based on either the prime factorization problem or the discrete logarithm problem. Both of these are considered to be secure as it takes classical computation and exponential time. However, this is not the case for quantum computing, as we'll see. So then for quantum computing basics, three really important concepts to understand are superposition, entanglement, and interference, as well as qubits, which are just quantum bits. So for superposition, that's the concept of having a quantum bit that is in a state that is neither 0 nor 1. So it's a superposition somewhere on the spectrum between 0 and 1. So it can represent all the possible values. This is quite important in quantum computing, as we'll get to in a moment. There's also entanglement, which is where two qubits are related, and then interference, where one qubit can interfere with another. Here's a visual representation of quantum and classical computing. So classical on the left, quantum on the right. As you can see, the unknown state of the superposition exists in the qubit, and then once it's measured, it will be either 0 or 1. So that's really important to understand that once it's measured, it will be 0 or 1. So we'll talk now about Grove's algorithm. So this algorithm reduces the complexity to search an unordered database to root n, as you can see there. So it takes an input, but it applies it applies a uniform superposition to all the possible outcomes and to all the bits, qubits, using a Hadamard gate before flipping the state of the entity that we are attempting to find. This is then amplified root n times and then measured. So the probability is not 100% correct due to error correction, but this will likely get the correct answer within the root n complexity. Then Shor's algorithm, which is definitely the most important in terms of quantum computing and cryptography. So Shor's algorithm effectively takes a guess and returns a much better guess at a prime factor. So for any large number n, you can take a guess at a prime factor being x. Now, as long as this is between 1 and n minus 1, this will work for Shor's algorithm. So after you take your guess of x, this will be raised to the power of all the register values, which exist in a superposition, and then this is divided by n. This will produce a register of r values that, based on their period, you will be able to understand the frequency, which will then be able to be used for f in the equation at the bottom, which is p equals x to the f over 2 minus 1. Now, the p here is a potential prime factor. To find the other potential prime factor that's related, you can, of course, take GCD with the inputs of p and n. Now, this doesn't work 100% of the time. It's roughly 37.5% accurate. However, that is still enough to make RSA completely insecure. So as you can see here, all the asymmetric algorithms, since they are based on either prime factorization or the discrete logarithm problem, both of which can be handled by Shor's algorithm, they become completely insecure in terms of their effective key length. Important to understand that this is not quite the case for symmetric algorithms. While Grover's algorithm does reduce their effective key length, it only halves it. So we can still consider symmetric algorithms quantum resistant as long as they have a sufficiently large key. Now, we will talk about NIST and the work currently being done to identify an algorithm that can be standardized, similar to the way that AES has been standardized. So NIST is currently looking, so as of October 2021, they've got a short list of finalists. These are either lattice-based, code-based, or multivariate. So here's a graphical representation. So we will talk further about Crystal's Kyber and classical Maclise. So Crystal's Kyber is a lattice-based public key encryption algorithm. It does not rely on prime factoring or discrete log. This is really important, as we discussed earlier, to be quantum resistant. So it's actually based on learning with errors problem. So this is considered to be quantum resistant for now. There's no known attacks, which is one of the reasons that it is being considered a finalist. So Amazon is already using this in industry within their Cloudflare WAF product. As you can see, it comes in multiple different key sizes, and the 1024 key size is considered to be as secure as AES 256. Then talking about classical Maclise. So the Maclise algorithm is code-based and is quicker and more efficient than RSA. However, the keys are much, much bigger. So the public key for Maclise is a random binary Gopa code, while the ciphertext has random errors added, which can be efficiently removed by the algorithm. Now, moving on, we need to talk about the future. So having an understanding that quantum computing is around the corner, probably 20 to 50 years away, we need to know now that our ciphertext can be intercepted, stored, and deciphered at a later date. It's also important to know that post-quantum cryptographic algorithms won't be pushed out overnight. They will take many, many years to be taken up in industry. So it's important to understand your data retention requirements and understand that you need to do as much as you can to make your current communication secure. Hopefully you've learned a lot about post-quantum cryptography today, and thank you for listening.